Hello everyone, I'm Mohamed Benmahdjoub. I'm PhD student within the bigger group and the Department of Oral and Maxillofacial Surgery at Erasmus MC. And my presentation will be about multimodal markers for augmented surgical navigation. So I'll start by explaining some basic concepts. Virtual reality is technology that allows the user to get fully immersed in a 3D environment and you can also interact with 3D objects in it, whereas augmented reality is the technology where you can still see your real world and project some additional information to it. A good example of that is the popular game Pokemon Go. So now I'll be explaining conventional surgical navigation systems, and I prefer to give it as an analogy of the application maps that everybody uses. So in the application maps, you have a representation of your real world with a map. In the surgical navigation system, you would use patient-specific data such as CT or MRI. When you use your maps, you plan your, let's say, target, where you want to go, and you get a trajectory to achieve that. And that's what surgeons do. So that, for example, in the picture that you see on the right, the surgeon can plan a drilling trajectory from the left to the right of maxilla. And then in the maps where you are moving along the planning, you can see your car in that world representation, and that's what the surgeon sees. So as you can see, this yellow stick represents the drill that the surgeon uses, and he can know where it is with respect to the patient. So to enable this tracking, Maps uses the GPS and data. And for the surgical navigation system, so for example, for the optical navigation system, you have stereoscopic camera using infrared, for example, infrared, that will track some reflective spheres. And with this, you can locate different instruments and also the patient. Another modality would be electromagnetic systems, where you have a field generator, and so it can locate every electromagnetic coil that enters tracking volume. So one of the challenges to this type of technology is the 3D perception. So while the surgeon is using this system, he tries to actually build the 3D aspect of the anatomy of the patient based on 2D images, which is pretty hard. And a second problem to this is the hand-eye coordination. So while the surgeon is performing the surgery, he's looking at the screen. So in this picture, the surgeon is trying to drill from top to bottom, but what he is on the screen is his drill going from left to right, and this is not that intuitive. So an example of how difficult is that is try to use your maps while you're holding your phone upside down. It's pretty difficult. So augmented reality is kind of a suggestion that was in literature that would help face these issues. So the research question in my work is having navigation systems, as I presented before, having an augmented reality device such as the HoloLens or mobile phone, and with the phantom or a patient, how can we project the CT data on the patient? So usually what people have done is use the same trick. So what they do is that they locate the head of the surgeon using those spherical shapes, and then if you define this relationship, you can project the CT data at the right location. But this comes with some issues, is that for each new device, you have to perform some calibration. So which means that you have to tell the system where these spheres are with respect to the screens. If you want to implement this method in an electromagnetic field, an electromagnetic tracking system, it's pretty impossible or hard. So the first issue is that you will have to wire your headset with this, and this constrains the movement of the surgeon. And also, given this very small tracking volume that you will be in, it would be hard to put the head of the patient, the head of the surgeon, and also the instrument inside that. And it would lead also to some electromagnetic inaccuracies. Sorry. So the proposed method that I'm suggesting is the multimodal markers. So what this consists of is a marker that can be tracked by two different systems. So for example, this one, what you can see is a QR code that can be tracked by the augmented reality device. and this one is the EM coil that an electromagnetic system can track. So going through a calibration procedure where you define the relationship between this sensor and this QR code, you get the spatial relationship between these two, and this actually would allow the augmented reality device, in this picture a camera, to know where the patient is. So this solution has some advantages. The first one is that this method can be implemented in both electromagnetic system and also in optical tracking systems. And also it is AR device independent, which means that if you don't perform the calibration multiple times, you perform it only one time. And if you have this relationship between the spherical shapes and the QR code, or the coil and the QR code, you would be able to actually project the CT data to whatever device that knows that special relationship. So to evaluate the system, there are three aspects of this. So because we perform this calibration using this pointer, so we want to know how accurate this pointer can be, and also to know how accurate we can compute this transformation. And finally, it's about the overlay accuracy, and this is the final output. So for the pointer accuracy, we measured 18 10-centimeter measurements on top of the whiteboard that I showed before. It has some divots that are known, that have known positions, and the mean average error was about 0.27 millimeter. And so for the calibration accuracy, so we try to define what would be the best calibration accuracy, and this is based on two parameters. The first one is the calibration surface. So we can, for example, calibrate only on this surface or the whole surface, and in addition, second parameter would be the number of points. So we can do a calibration, let's say 4 points or 12 points or 24 points. And then after we compute the calibration metrics, we can then compute the shift and the error. So we performed this 5 times for each scenario. So for 4 points, for 12 points, for 24 points, and for 200 millimeter square and 400 millimeter square. And then what we got is that if you perform this calibration on 12 points and in a surface above 200 millimeter square, you get an RMSE error of 1.5 millimeter. So the final aspect of the evaluation is the overlay accuracy. And so what we did is that we captured different pictures from the camera at a known location from 50 to 60 centimeter and on different angles, 20, 45, and 90. Then we considered the first metric for evaluation is the intersection over union. So what we do is that what you see on the bottom picture is that we overlay the city data, we segment the real image, and based on that we compute how the 3D model overlay on the real one. And so for that we picked three different calibrations, and so C2 is better than C1, C3 is better than C2, and then what we can see here is the percentage of how good the overlay was. But now the problem is that you can see that it's not very informative. So for example, from C1 to C2, you can see only 2% of improvement. So what we did is that we went for a point-based approach. So what we do here is that there are these projections, and we know where this position is on the CT data, and we perform some annotations to measure this distance between the expected position and the real position. So what we see here is that under certain conditions, we can get an accuracy of 2.3 millimeter, for example, in here for 45 degrees and the best calibration. But here the problem is that you can see that there is an issue with at the 90 degrees, and this was because there are some intrinsics of the camera that weren't known at that point. So I want to show the, let's say, demo of this solution working. So this is the pointer I was talking about, which is tracked by field generator. This is the phantom skull with the 3D data following the movement. And you can see also that we have a collaborative view. So the view that you see here is from a webcam, and this one from the same solution implemented over a smartphone. And all it needs to know is this spatial transformation. So to summarize, of what I presented here is a solution that is tracking system independent, that would align AR systems with surgical navigation systems. The system was technically evaluated, and it's provided some acceptable accuracy in their certain cases. So the advantages of this solution is that it allows the marker to be moved around the scene because it's tracked by the navigation system. You perform only one-time calibration if the special relationship between the EM sensor and the QR code is known, and it would also allow some easier collaboration between different devices. And thanks for listening.
Okay, thank you, Mohamed. Very interesting and inspiring presentation. And I don't see any questions from the audience yet. So if there are, please put them in the questions and answers area. But I do have one or two questions for you. Perhaps, as you know, also in Utrecht, we have some experience with augmented reality in brain surgery. And of course, the accuracy is one of the big issues. With your results now, how far do you think you are from clinical application, and what are the challenges to get it there?
I think that's one of the challenges. So, for example, this solution would work on rigid transformations. So if there is any deformation, it would be hard to see that. So, for example, if there is a brain shift, this wouldn't work. This actually was first designed for, let's say, more bony kind of structure applications. But then how accurate it needs to be, I think it depends on the surgical application. So, for example, in some of the spine surgery, it would be okay to be shifted by 2 to 3 millimeters. But there are some other surgeries that requires way more accuracy, like 1 millimeter or even better. So I think it depends on the application that you are targeting.
Okay, and time-wise, have you any clue in how many years, months before we get this technology into our clinics?
Honestly, I think it still requires more time. I think like the augmented reality is going forward, but it's still not working for the clinical part because, like, for example, you have a lot of algorithms, vision algorithms that will deal with alignment and all of that, but you can't implement them inside OR because you have draping, you have a lot of other difficulties. So I wouldn't be able to give a specific number, but I think we are still far from that. I still think we need more work on that.
Okay, thank you. I see one question from the audience popping up now. Is there a potential of, I think he meant electromagnetical disturbances with other OR devices when we bring it to the OR? Did you look on that, or is there none case whatsoever?
I think there are people that are using it already, even for brain surgery, because, like, for example, the good thing about EM is that you don't need a field of view. You don't need a direct line of sight. And so if the sensor is hidden, is inside some anatomical structure, or for example, the nose or whatever, you can still know where it is. So there are still applications that use EM. And when it comes to instruments, getting inside that specific volume, tracking volume, it still works. And I think, yeah, it still also depends on how accurate you need that to be. But yeah, it's used in clinical applications.
Okay, thank you very much.